Chapter 7 is all about inductively supporting or confirming hypotheses. There are a variety of ways in which the word hypothesis is used in English. It can mean a guess or suspicion that something is the case, without any proposal to test that suspicion. Or it can refer to a belief that is not supported or not yet supported by evidence. In this chapter, those are not what we mean by a hypothesis. In this chapter, a hypothesis refers to any sentence that we want to test by determining whether predictions that follow from it are true. In the right circumstances, true predictions offer inductive support for the hypothesis and are said to confirm a hypothesis. Predictions that turn out to be false disconfirm, that is, inductively undermine a hypothesis. In this chapter, we will be examining different methods by which people attempt to confirm a hypothesis. The first such method we'll look at is the hypothetico-deductive method. I'll say right off the bat, the name hypothetico-deductive, not very informative for what the approach is. It's not really an deductive method at all, so we'll just let that misnomer stand. But just don't try to figure out the meaning from the name. On the simplest version of the hypothetical deductive method, to see whether a hypothesis is true, derive some prediction from it. If the prediction is true, then the hypothesis is confirmed. If the prediction is false, then the hypothesis is disconfirmed. We'll see that most actual implementations of the method are more complicated than this. But for now, we'll look at this really simple model as a good place to start. Okay. So take the example of Ptolemy's geocentric model and Copernicus's heliocentric model. This is an example that comes from your book. During the time of Galileo, both theories were out there, and different individuals cited different kinds of evidence in support of the different views. Now, Galileo came along with his telescope and made the prediction that he'd be able to see Venus in phases through the telescope. By that, he meant see phases like we see with the moon. It can be a crescent or a gibbous or what have you. His prediction was that if the heliocentric model was right, then we would see these phases. So, on the basis that he was testing the heliocentric model, he was looking to see if we had evidence that Venus showed these phases. Okay, so Galileo's hypothesis. The Copernican heliocentric model is correct. A simplistic expression of this argument showcasing the hypothetico-deductive method would be as follows. Premise 1. If the Copernican system is correct, then Venus will show phases. Premise 2. Venus shows phases. This was the data that Galileo collected when he looked through his telescope and saw the phases. Conclusion. Therefore, the Copernican system is correct. Normally, arguments for hypotheses are intended to be inductive arguments, not deductive arguments. The truth of the premises in inductive arguments never guarantee the truth of the conclusion. So it's not as if Venus showing phases deductively proved that the Copernican heliocentric model is correct, but it did confirm it. It did provide support for the view. Confirmation refers to positive inductive support rather than to a guarantee of truth. So the question we need to address is whether, in arguments for the inductive hypothetico-deductive form, the premises lend probabilistic support to the conclusion. Do they? If we consider the hypothetical deductive argument in the simple form we saw it in a moment ago, the answer to this question is not enough. This answer is less distressing than it might seem, however, because the actual form of reasoning used by scientists to confirm hypotheses depends on additional premises not recognized in this preliminary version of the method. So let's go ahead and start looking at some of those complexities now. Well, actually not quite away. First, I want to just briefly talk about what a conditional is. Conditionals are types of sentences. The sentence, if the Copernican system is correct, then Venus will show phases, is an example of a conditional sentence. Conditional sentences are sentences that express a relation between two conditions such that if the one situation is the case, then the other situation must be the case too. So the conditional we saw earlier was if Copernicus's heliocentric model is correct, then Venus will show phases. If the one situation obtains, then the other must be the case too. So if throughout discussions in this chapter we talk about conditional sentences, this is the type of sentence we're talking about. We're going to cover conditionals even more when we move on to chapter 8. Auxiliary hypotheses. Auxiliary hypotheses are hypotheses used in conjunction with the hypothesis being tested to derive observable predictions. Auxiliary hypotheses are not always explicitly stated and are assumed to be true in the context of a test of a main hypothesis, although they themselves can be tested in other contexts. There are two important types of auxiliary hypotheses. One type has to do with proper testing conditions. Hypotheses of this type are concerned with whether all the equipment and material used in the test are in proper working order, and whether the observers are capable of correctly assessing the outcome of a test. In short, they are hypotheses that the means by which the hypothesis is being tested are good. The second type of auxiliary hypothesis comes from theoretical background knowledge. Hypothesis testing is carried out against the background of presumed knowledge, for example, such as the knowledge that Venus is between the Earth and the Sun. Various theories or select parts of theories function as auxiliary hypotheses when they are assumed to be true in the test of another hypothesis. In our previous example of Galileo's prediction about Venus, one of the auxiliary hypotheses of the first type was that the telescope provided reliable data about what was observed through it. This auxiliary hypothesis was called into question by some proponents of the geocentric model, of Ptolemy's model. So that was a lot of information I kind of just tossed at you. The basic point, auxiliary hypotheses are those background assumptions that both groups kind of take for granted. So for example, in the case of trying to prove the heliocentric model, confirm that over the geocentric model, people on both sides of the issue thought that Venus was between the Sun and the Earth. The question was just which one was the center, Sun or Earth, and which one was further out. But they both thought Venus was in between, so that functioned as a common background assumption. Also, in the case of the proper functioning of materials and equipment, that's an assumption basically that there's just some kind of general correctness about the methods by which the observations are collected. So, if you really want to confirm a hypothesis, you have to assume not only that your hypothesis is true, but all the auxiliary hypotheses that you have as well, you have to assume that those are true. Because if one of those is false, that might throw off the relationship between your hypothesis and your predicted outcome. So the more complex form ends up looking like this. If H, where H stands for the hypothesis we're testing, and A1 through AN, which stand for all the auxiliary hypotheses, are true, then P is true. P being our prediction. Then if we collect observational data that tells us, look, P is in fact true, then you conclude, therefore, H and A1 through A1 are true, or, if you want to be more exact, they're at least confirmed by the data, inductively supported. Something else we need to keep track of, in addition to auxiliary hypotheses, are alternative hypotheses. Alternative hypotheses are hypotheses that could yield the same observable predictions as the hypothesis being tested, but which are distinct, that is, make a different claim than the hypothesis being tested. Ptolemy's geocentric model didn't count as an alternative hypothesis to Copernicus's heliocentrism, at least not in the way we are using the term alternative hypothesis. The reason why it didn't count as an alternative hypothesis in this sense is because it didn't predict that Venus would have the type of phases that were observed. In the technical sense that we're working with alternative hypotheses, they only count if they also could yield the same observable predictions. However, Tycho Brahe had come up with a second geocentric model, and the Tychonic geocentric model did predict that Venus would have phases. Thus, the Tychonic model, which was distinct from the Copernican model, in virtue of also predicting that Venus would have phases, counts as an alternative hypothesis in relation to the evidence that Venus shows phases. So, how are we to decide which view to accept when more than one hypothesis fits the data, as in the case of the Tychonic and Copernican models of the solar system? One option is to see which hypothesis was more plausible before the test, before we ever ran the experiment. That is, to see which one had a higher prior probability, and to say that the one with the higher probability is the one confirmed by the test. If we think of tests as resulting in an increase or decrease of the probability of a hypothesis, rather than as settling its truth or falsity, then a test, and I would advise thinking this way, by the way, then a test that supports two alternative hypotheses equally well leaves their probabilities relative to one another unchanged. In other words, since either alternative could account for the result, the one that was more probable before the test observation remains more probable after it. On this view, the prior probability of a hypothesis, the probability that the hypothesis is true prior to taking account of some test of that hypothesis, is important in the logic of confirmation. Not only do these probabilities help us decide which hypothesis among several alternatives is confirmed by a particular test, they also help us to decide which hypotheses are worth taking the trouble to test. So, for example, if something has a prior probability of almost 0, meaning it's really, really implausible, we're probably not going to bother testing it. But if it's got a reasonably high prior probability, it's more likely to be worth the effort of testing. There are a variety of means by which a prior probability can be determined. In some cases, only roughly non-quantitative estimates of prior probability can be made. In others, precise quantitative values can be assigned. Okay, so now that we've talked about auxiliary hypotheses and alternative hypotheses and prior probabilities, let's look at kind of a more fleshed out version of the form of the hypothetical deductive method. On this more fleshed out, accurate form, the first premises is that the hypothesis is initially plausible. That means it at least has some degree of prior probability. We don't think it's near impossible that the hypothesis is true. We probably wouldn't bother testing such a hypothesis. Second premise, if the hypothesis and the auxiliary hypothesis are true, then the observable prediction is true. And this was the premise we saw before when we looked at the hypothetical deductive method right after talking about auxiliary hypotheses. Premise 3, the observable prediction is true. And premise 4, no alternative hypothesis has as high a prior probability as the hypothesis that is being tested. From this we conclude the hypothesis is true, or at least we can conclude that the hypothesis is more likely than the alternatives to be true. Alright, so that's our start on probability and confirmation of hypotheses. In the next chapter, we're going to talk more about confirming the next video, we're going to talk more about confirming or disconfirming hypotheses.